In this video, I'll show how to transform an equation from polar to rectangular form and vice versa. So let's first start by talking about kind of the building blocks for polar form. So if we have a right triangle labeled xy, the hypotenuse is r, and we have the central angle theta, we could give this point up here as x comma y, that would be in rectangular coordinates. We could also give it in polar coordinates with r comma theta. Remember, r is the distance from the origin and theta is that angle. So we can come up with a few different relationships that will show kind of the function between polar and rectangular. So cosine of angle theta, we know, is x over r, and then if I solve that for x, we could say x is equal to r cosine of theta. So x is the rectangular coordinate, and then r cosine theta would be in polar form. We could say sine of theta is equal to y over r, and again, if we multiply both sides by r, we can write y is equal to r sine of theta. And then looking at the triangle, thinking about the Pythagorean theorem, we could say r squared is equal to x squared plus y squared. And then the last relationship we want to remember is tangent of theta is equal to y over x. So these are the building blocks of what we want to remember when we're trying to convert an equation from rectangular form to polar form, and vice versa. Okay, so let's rewrite this equation. X squared plus y squared is equal to 9 in polar form. This isn't necessary, but this is an equation of a circle, has a radius of 3, and it's centered at the origin. So let's rewrite this in polar form. Well, what we just saw was r squared is equal to x squared plus y squared. So we can rewrite this as r squared is equal to 9. And typically when we rewrite an equation in polar form is we would like r to be as isolated as possible. So r is going to be equal to plus or minus 3 here. And that's it. So that one's pretty straightforward, just one substitution. Let's look at one that's a couple steps. So let's rewrite x squared plus y squared equal to 6y into polar form. Well, what we just saw is this can be rewritten as r squared is equal to 6y. Now because we have both, or because we still have a y variable, this is not yet in polar form. Polar form should only have r and theta, no x's or y's. So we need to take care of that y. Well, y we can rewrite as r sine of theta. So r squared is equal to 6 times r sine of theta. And we want to solve this for r. So let's see what we can do. 6r sine theta. To solve for r, because I have r in two terms, two separate terms, I'm going to write all the terms on one side and then factor out the r. Okay, so I'm going to get r is equal to 0. R minus 6 sine of theta is equal to 0. So r is equal to 6 sine theta. So both of those equations would give us the same graph of this equation. And what, didn't mention this, but our original equation in rectangular form is a circle. And these equations that we came up with in polar form will also give us a circle, but this is just a point, kind of. It's a point, but the point is 0, 0. And then, so we don't really need to consider that. and then r sine of theta is the equation, and if we were to graph this, this would also give us a circle. Now the question is, why does this give us a circle? So let's come up with the graph of what that looks like. Okay, so if we wanted to graph this, we can do that just by plotting points. I'm going to write the theta first here, just because I'm going to input a value for theta here, and then I'll get an r value as the output. So the easiest values to pick for theta are going to be values on the unit circle. So if theta is 0, sine of 0 is equal to 0. 0 times 6 is 0. Sine of pi over 6 is equal to 1/2. 1/2 times 6 is 3, and so on. All right, so here are all the values for theta equal between 0 and pi. And I've listed all the coordinates when I plug in theta into the equation. So let's go ahead and graph this. Okay, so hopefully you can see what's happening here. So when I enter r is equal to 6 sine of theta, I get this graph of a circle. And let's just see how this makes sense. So let's start actually at this point up here. That angle is pi over 2, right? If I'm starting here and going in this direction, pi over 2 is going to be the point that I plotted, and that distance is 6. So that corresponds to this right here. Okay, 0, 0 is a point. Let's look at this right here, pi over 6, comma 3. So pi over 6 is this angle, and 3 is 3 units outward from the origin. So those ones are the easy ones, the ones that come out to be integers. Moving down, pi over 4, well, that's this angle right here. And 3 square root of 2, well, square root of 2 is about 1.4 times 3 is a little bit more than 4, and that makes sense. So what's happening is all of these points are on some of these angles, and then we could draw through a smooth curve here. So all this to say, this equation we came up with, r is equal to 6 sine of theta, does in fact correspond to what we originally had, which was x squared plus y squared is equal to 6y. All right, and then let's do one more. Y is equal to 3x plus 2 in polar form, or we want to write that in polar form. Now, we can rewrite x as cosine of theta plus 2, and we can rewrite y as sine of theta. Sorry, r sine of theta, r sine of cosine. Let me fix that. 3r cosine theta. Okay, now again, what we want to do is ultimately rewrite this as r equal. So I'm going to group all the r terms on the left-hand side, factor out the r, and then we can divide by what's in the parentheses. So we end up with r is equal to 2 over sine of theta minus 3 cosine of theta, and that would do it. And if we were to graph both of these equations, they would both come out as lines. So that's a line, and this is also a line here. Now you might be thinking, well, why do we care about doing this? Well, in calculus, once we start doing integrals of different areas, it makes things a lot easier if we're setting up integrals and solving them if they're in polar form versus rectangular form. So we need to be able to take something that's in rectangular form and rewrite it into polar form. Okay, and then let's go the opposite direction. Let's start with an equation in polar form and rewrite it in rectangular form. Well, in polar form, we care about, or we have relationships for sine, cosine, and tangent. So I'm going to rewrite this as 2 over cosine of theta. if I multiply both sides by cosine of theta, our cosine of theta is just equal to x. So this is x is equal to 2. And that's just a horizontal line, or rather a vertical line, through x equal to 2. And then let's do one more here. Let's rewrite r is equal to 3 over 1 minus 2 cosine theta in rectangular form. Sometimes you might see this instead of rectangular form as Cartesian form. So what I'm going to do is I'm going to multiply both sides by 1 minus 2 cosine of theta equal to 3, and then I'll, let's see, what do I want to do from there? I guess I'll multiply that out. And r cosine of theta is x, so r minus 2x is equal to 3. And then if we add the 2x to the right side and then square both sides, that's useful because r squared is equal to x squared plus y squared. So x squared plus y squared is equal to, I'm going to rearrange 2x plus 3, and that's squared. Okay, so that's good enough. At this point, it's not clear. It's not really in a standard form of any type of equation. We could go a little bit farther, though. If we said x squared plus y squared is equal to, when I multiply or expand this out, I'm going to get 4x squared plus 6 plus 6 plus 12x plus 9. So if I get all the terms to one side, I could rewrite this as 0 is equal to 3x squared minus y squared plus 12x plus 9, and that the graph that's represented by that equation is a hyperbola. And that's it.